overlays, what are available. And then we discussed fundamental cases, which are described by equations, stationary simulations, like always, is the basic thing you usually do. What happens if transient things are decayed? Then, of course, in certain situations, we started talking about stationary simulations. We did a demo model. If you followed what I did together, otherwise you just got it demonstrated. That actually was the first step into a topic which we didn't completely finish. If you do stationary simulations, you basically are interested, or in many cases you are interested. Here, some of our artwork remained, I just noticed now, over a week, so nobody used it for a week. The mechanical stress is something people are interested, for example, to make sure that there is no overload, that you are far enough away from parameters I just mentioned before, that you not come close to the region where plastic deformation may happen. Stress, strain is another parameter, and particular the concept of strain is at the end not so simple as one might expect from some concepts you certainly are familiar with, but there is a bit more, and we started discussing this, and I didn't resolve the whole thing, but I tried to give you an idea why we have a topic here. So we will finish this thing, and then there are other study types, basically that different fields here result in different study types, so time-dependent simulations, and then harmonic simulations, eigenfrequency simulations. I just realized geometric nonlinearity, that is something we started discussing, and I try to motivate what is the problem. You may remember from the demo, we set up a model. It was very simple with two squares, very simple geometry, and we moved that squares, maybe it was also scary, we moved by a certain rotation angle around that fixed point, so a certain rotation angle. The way we did it was with a rotation matrix, but this is just a tool to do it. And we did it for the two squares, so that is obviously some movement. Movement, to put it in a more precise way, a displacement. So what you basically do in mechanics, in all of these cases, we have an equation which provides us information about displacement. Displacement, just to remind you, is actually a vector quantity that consists of three components, usually u, v, w, x, y, z. So obviously, if we rotate the thing with a prescribed node we use for that, we would not expect to see something like mechanical stress or strain. Why should there be anything like this? If we have a solid and we just rotate it and not making other type of things, there shouldn't be any stress, any strain. I configured the two squares in a little bit different way. Basically, one of them I configured in a way which was related to a definition of strain, which is commonly called engineering strain. That is a simplified way of strain, which is very closely related to things you probably know about strain, the concept of strain. And there was another way to configure it, discrete Lagrange strain. And it turned out, if we do these rotations for both of the squares, one of the squares behaved as expected. They just moved, just got rotated, no stress, no strain, why there should be anything. But with the version of engineering strain, there was a lot of strain, so something is wrong, obviously. And this thing we just continue discussing and runs under that headline, geometric nonlinearity. I'm aware that things, if you hear it first time, may be a little bit confusing. I know because it happened to me the same way. I'm not a mechanical engineering guy, so when I heard it first time, I thought, what is this? Why we do this? So you just have to dive into this. Maybe some of you heard about this before, then maybe easier. Anyway, we try to do it in a way that all of you should be able to grasp the concept. And grasp the concept means, first of all, understanding the problem, where it's coming from. At the end, I will also talk a little bit what we do when we have the displacement, are able, or COMSOL is doing this for us. We just try to understand it a bit better in stress. What we do with this stress results, we can do certain calculations, evaluations with this. There's nothing spectacular, you already know this thing, I guess, like Van Mises stress and main stress. I already displayed that slide last time, but just to quickly remind you, the physics modes available in COMSOL. This is what is prepared. You always can do more by typing in your own equation, but then it usually becomes, at least for beginners, more complicated. So most people which start with COMSOL using this physics mode. So there we have single physics. Single physics in that case means solid mechanics, with some specialities, shells, membranes, so certain geometries which would cause challenges for the mesh. If you have a thin layer, you can mesh it, but that's not so easy, and COMSOL put here certain elements which are actually neglect the thickness, so it's basically a 2D structure, but then of course they have to do certain things to take into account the thickness, the thin thickness. Anyway, then we have multiphysics, solid mechanics combined with other physical aspects. Classically is temperature aspect, and we've got thermal stress, thermal elasticity. Joule heating takes another physics aspect. You know it from our beginning model. We then in addition have heating caused by an electric source at the current flow. Piezoelectric, piezoresistivity, and electromechanics. I think I gave examples last time. This is something you would use for MEMS switches. So, if you set up the model in the wizard, the final step is always you select the study. And I recommended always start with a stationary simulation. And that is the first thing we also started discussing regarding the physics equation behind it. So if you select stationary simulation, that is the basic equation. And to get a bit familiar with this thing, we got this, or we did this demo mechanical loading of a flat bar. I explained a little bit. So we set up that model, which used this equation, just to get you familiar with this. And then we did this second demo I already explained there, which was to show you that there is an issue with the strain, and we have to find out a bit more about this. I think I also quickly showed that slide, but just to get started again. Basically, you saw that equation for static behavior just a second ago. And with the things we discussed before, this equation maybe makes sense immediately to you if you would read it in the sense that this quantity we are addressing here, we ask the question, has this quantity a source? In that case, the quantity is stress, mechanical stress, and the answer would be, yes, it has a source, and in fact, it's a force applied to the material. So that makes sense, according to what we discussed in the lectures before. There is one thing I try to put your attendance to. So far, when we use this equation, here we always had fields, vector fields. But this is not actually a vector field, it's a one dimension higher, it's a stress tensor, because it has 9 components. So it has a stress in x, y, z direction and combinations. So it's a bit more complicated structure, but the idea is the same thing. Then let's come back to the meaning of that equation that just says if you have some stress in your material, that results because there are forces acting on the material. Volume forces means it's a very general way to write it. The force can be different on every part on that solid. I mean, if you start talking about this, you have simple forces like a pressure acting on that surface, then the force is actually equal. But you can have more complicated things, and to have it very general, that is a volume force. That means Newton per cubic meter. Maybe just to get familiar with this thing, let's check the units. Here we have Newton per cubic meter as SI unit. This is stress. What is the unit of stress? It's the force on the area, so Newton divided by square meter, that's stress, pressure. And what was this? You remember that is the operator just doing a derivative. It has 3 components, that's why it is like a vector. So what are the 3 components? These are derivatives regarding the x direction. There is a short writing, maybe I just use it. You saw what it actually is, but sometimes you write it in such a way that it's more easy to write it. In terms of units, what does it contribute? If you do the derivative of the operator, you get another meter. So that's what you should also expect. So we have Newton per square meter on both sides, fortunately. In a way, this is just something you know from basic Newton physics, that is a balance of force. If you put that force on the other side, you could also say the sum of all forces is 0. That was one of the Newton laws, the very basic Newton laws. Depending on which forces are involved, so because we have no dynamics here, there is only that volume force and the response to this as a stress. Seems simple enough, but unfortunately it's not completely simple. One of the things I try to address here is we have an equation, we saw it when we set up the models with DMO, which solves for the displacement. So there should be an equation which contains the displacement u, but it's not seen here. Particular displacement field. Now we have to take into account another thing which is special to solid mechanics. We're not bothered by that topic with other physics like thermal effects or current, electric effects. We have different frames. We have the material frame. That one is the material frame. That's the undeformed solid. And once volume forces are acting, it gets deformed, and by getting deformed, it also gets displaced with displacement field U. So I wonder if I don't have the names here. They're just on the next slide. What are the next slide? Anyway, I don't need the name. I just meant that is called the material frame. It's undeformed, and that is the frame after applying the volume forces. So the coordinate system for the material frame, the undeformed, is labeled with large capital X. The deformed geometry is small x. So you see that particular point here, which is labeled with large X, after applying the force, it gets displaced by the displacement field or vector U, so it ends up being here, just moved from here to here. And then in the deformed frame, it gets the coordinate small x. It was previously large x, gets displaced by U, ends up at small x. That is, I think, simple. There are relations between the spatial coordinate and the material coordinates. Particularly displacement field U, that vector can be calculated from x and then not plus large X, because we have to reverse that vector error to have it like this, plus this would be this. Just vector calculus. We need these relations later, you will see. Now, where is U in the PDE? We're still looking for that answer. A first step, which is not the final step, is that the stress is calculated or related to the strain. A simple version, a very simple version of that I put here on the paper, on the whiteboard last time. The most general way to write it down would look like this. So what the heck is this again? We have here this strange symbols. The reason why it looks so a bit unusual, it's not division, it's not the division sign. That is a multiplication of a, here you see, no you don't see, where did I put it? It's a fourth rank tensor, so sounds terrible. So that is it's not only a matrix, it's not only a cube, it's even one dimension higher. I will show you later how that thing looks like. I mean, if it's 4 dimensional, you cannot even display it. So there is a notation, Vogt matrix, you probably heard about that. And in many cases, you can write it more simple. For certain types of materials, at least you get not only the Young's modulus, but also the Poisson ratio. You can even more. So basically, this is Hooke's law, which relates the strain to the stress. In a very simple situation, would look like this. At the moment, we should not be concerned too much that this is something more complex. Just for having some idea in the head, I would recommend maybe at the moment think like this. Anyway. We now have an equation which is for strain, but still not for the displacement. But you already guessed there must be a relation, finally, between the displacement and the strain. That's what we're heading to. I will finally give you the correct equations for a 2D geometry, the one you see here, but I like to go one step before and explain the things in 1D, just to get familiar with the concept. So reducing from 2D, which is this sketch, to 1D, the situation would look like this. Everything goes on in one dimension. I choose the x direction here. So we're considering that particular point here in the material. The material in that case is just a rod in 1D. So you might recognize the black line starting here at the origin of the frame and ending somewhere here. So on that rod, I consider a particular point. In 2D, it would be, of course, a 2D structure, here a 1D structure. But the point I'm considering would be here, labeled by large x, as labeled here by large x. This is the material frame, the undeformed, before applying a force. And at that particular point here, I consider a little piece of material which extends dx, d large x, d capital X. You see, there's already a difference. I mean, here in the 1D case, the coordinate direction is aligned with the particular element of the rod. Because we only have 1D, there's no chance to be a misalignment. Here we have a misalignment. The vector describing the position is differently oriented than the vector of that little piece of element we are considering here. So now applying a force to make something like this would result in something like that. Of course, if you pull on the rod, you should fix it somewhere, otherwise it doesn't make sense. We pull on that thing with the force Fx. We only can pull in x direction. So just to make it clear, I label it like this. So what would happen if we try to follow for the point which originally was here? It moved up a bit higher because of the stretching. So that point moved from originally x by how much? That's the same thing as you see in 2D. I tried to make the relation because later we of course discuss it here so that you have the relation available. So that particular point moves from here to here in 1D from here to here. That's the one thing. The little element originates. It's of course much smaller than I show you, but I have to draw so it has a much more length than it would be in reality. It would be very, very small in reality. But anyway, we stretched the whole thing, so that little element we were considering here is also stretched. It's a bit longer. Now, what can we do with this? First of all, I like to notice that the relation we saw here before u is large small x minus capital X, of course, also holds here. If we take that dimension, how the things are related, obviously like that. I mean, here at 1D is very simple. The deformed coordinate is the original plus the component of this displacement vector, which is just u. So now let's come to our strain object. Before this, I make a little reformulation. Now it's actually similar to what I showed you before. If you, it's obvious, I don't have to say too much about this. Now, I wrote down that expression for the strain in that situation, 1D, so I labeled epsilon x. Does this make sense for you? That is the concept I used here, which you should be familiar if you talked about strain so far. Maybe to make it very clear, sometimes I think people talk about this topic of strain about a rod, which is fixed here, which has originally length L0, and then you pull on the rod to make it a bit more longer, so it ends up to being then length L. And then you would write down that the strain is the difference from the original length to the final length, which would be the stretched length minus the original length divided by the original length, some definition lengths. And that you may also call delta L. So it's delta L divided by L0, if you are familiar with this. And this is actually what you also find here. But now we talk about just very small length, not a rod of 1 meter, very small. That is because we actually want to know the stress, the strain at every point. So it changes. So we cannot talk about 1 meter, doesn't make sense. But it's the same concept, the same simple concept. So what you can do with this, you can take the derivatives in front. This is just a reformulation. And then, referring to this here, you see that difference is nothing but the displacement. So you can replace it. And now we arrive at a kind of important result. You see that the strain used to calculate the stress, inserted here in that equation, somehow is now dependent on the displacement for that particular situation. Later we will see this is exactly what we call engineering strain. And as you saw with the example, that is not the whole story. That can cause problems, or will definitely in certain situations leads to very, very wrong results. I come back to that result later on. So we have a derivative, we have the displacement, our main variable, which was temperature for heat problems and so on. From here it goes to strain, from strain it goes to stress, and then we are in the equation. So then that's an equation for the displacement. For that ongoing discussion, I make a little rewriting of that part here. You will maybe or hopefully see later why I do it here. Maybe at the moment it doesn't make sense. What I have done here is just rewriting this as dx over dx minus dx over dx. Sorry, skipping capital and small. You see what I mean? So that gives -1. But the interesting part I will make use of and try to get you familiar with here already is that the stress is somehow also related, it's just a different way of writing, by having the derivative of the spatial frame coordinate with regard to the material frame coordinate. So we have this type of structure. So somehow that is something which relates, in 1D this with this, and in 2D this, and now we already get a rotation in here with this. So let's continue discussion with this. Later on it turns out that thing is called, of course it has a crazy name, deformation gradient tensor. But the concept behind is not so difficult to understand. That is somehow something which describes how I get that element after deformation in that position. So now I explain the same things I did before with 1D, now in 2D, and it gets a bit more complicated, and then we see what is the point and solve the problems. The relation between that spatial frame dx and the material frame dx I rewrote like this. And then this is nothing, just, you can call it a transformation. if you know nothing about this, but how that piece of material, after applying the forces, ends up in the spatial frame. If you rewrite this in that way, we just get the same structure as we saw before for the 1D, and that's the transformation gradient tensor. If you try to rewrite that expression, now we have to step by step just recognize things which are not difficult but just geometry. How to come from here to here? What did we do? We replaced x, small x by capital H, x plus u. Capital X plus u, the same thing. That x is capital X plus u. So this is in the brackets. And then if we take the derivative for this, I mean, now we have vector quantities, but it has to be a bit carefully, but anyway, dx over dx is still 1, but what does that 1 means? If we have vector quantities here, maybe at least you can guess, that's the unity the unity matrix. So in 2D, that thing, just to also write it explicitly, what is the result from that is a 2D matrix looks like this. That results from d capital X after d capital X. And then we have, I mean, this is the derivative we discussed before here. Somehow it's also a vector applied to the displacement vector, so that would look like this. It's just another way to write it. At least it looks a little bit like this. I mean, we encountered this structure, you remember, the Laplace operator combined with a quantity. We previously called it a gradient, you remember. If this was the temperature, then we called it a gradient. But we again have to be carefully. This is not a scalar quantity, obviously not, because it has a vector. So it's a little bit the same thing. Here we moved from a vector to tensor, and now we have something, if that would be temperature, we would call it a gradient, but now it's a vector quantity. Previously, the vector quantities we combined with a scalar or cross product. But this is another thing which is not trivial. I already started talking about like this. I'm aware you have to adjust to this, maybe slowly, but this individual steps, I try to boil it down in such a way that you can follow step by step by step, and probably afterwards you have to read it again if you want to really understand it. No, we have to talk what is the result of this. You may already have an indication. I mean, if this part results in a matrix, 2 by 2 matrix, you cannot have a matrix combined with a vector or a scalar. That should also be a matrix, shouldn't it? Shouldn't it? Otherwise it doesn't make sense. This is like having different units in a line. So why this is a matrix? This Nabla operator I just rewrote like this, so you are familiar with this. Now it's even the more the more explicit writing, d over dx, d over dy, d over dz I skipped because we're just considering 2D at the moment. It's complicated enough. And the vector, the displacement vector, you see this is a, how's called, a color vector, that is a row vector. We just go a different way. And that makes a difference. If you, at least by definition, if you have it combined that way, then the result is a matrix. So the resulting matrix, I just wrote down here. So you can figure out how this combines to that matrix. So the actual meaning of this is a matrix looks like this. And maybe at this moment already, you may realize, or maybe I have to go back. I think I prepared on the next slide. Let's continue working with this structure. maybe to summarize before we're leaving, how we came to that. I gave you a 1D interpretation of what is happening in 1D for such a small element of the material by applying force. And using the coordinates as defined, somehow we have a relation between the small element in the material undeformed frame in the deformed spatial frame. However this is made, we call this a transformation. We don't care how that exactly is done. We see it afterwards. We just call that a transformation with this fancy name. And that is just what is in here. The element in the undeformed frame is transformed in the element in the spatial deformed frame like this. Starting from here, we can rewrite, and then we see we have these derivatives. Then we rewrote the spatial frame coordinate x with the material frame coordinate capital H in the displacement, just the relation of that triangular geometric relation. Then we found out that this is the identity matrix, and that thing here looking like a gradient, if that would be a scalar product, is actually also a 2D matrix. So let's continue work with this. It's just a rewriting, nothing new here, just in short form. We ended up here that the deformation gradient tensor is actually something like this. And there is a relation to something I try to give you a feeling for with the 1D example. You see this here, du over dx. That was exactly the form which we got in our 1D example for the strain in the x component. So dO over dx. Just note, it just looks the same. So it maybe gives you a feeling, or maybe a feeling kind of convincing that what we are doing here is going toward strain. At least we find something which was previously in the 1D case exactly what you would understand if you talk about strain. I already deleted here classically the 1 meter rod. We pull a little bit, shows up here. And we have it in the x direction, or called u, and the y direction called y. And here maybe some movements. If we act in the x direction, it makes a movement in the y direction. So we need something like the Poisson ratio. That is where the Poisson ratio would came in. But I mean, why we have an identity matrix? Not so clear, but that seems to make sense and is obviously somehow related to strain. The way strain finally is defined, you see here. So somehow we use this F, which contains element, which makes sense to us, F, but we do a bit more. We combine that F with F transformed. Keep in mind that is a matrix. What means transformed? We just flip the off-diagonals. So why we do this? I mean, maybe we could have a definition of strain, because here it seems to make sense. The reason why we do this is related to the fact we saw with our squares, which we rotated. Maybe before explaining the math behind it and give you some more information, without math, I may explain what is the problem. The displacement going on in that particular example, first of all, moves that point from here to here, but there's also a force component which lengthens that little element. So you see, basically we have two types of displacements. We have a translational displacement, and we have a rotational displacement on that thing. The translational, the stretching part of the movement that makes the thing longer, which causes strain. But some part of the movement which just doing the rotation, that of course not results in any strain, in any stretching. That was the situation if we could make a movement. Here you see that it's deformed, but we could make a movement, what we did in the little demo, we just moved that thing here, be not deformed at all. But also this movement obviously is described by a displacement coordinate, but that should not result in strain, obviously, yeah? Because if we just move it, just the part which pulls in the according direction, that should be counted, obviously, for good reason, to be strain. And we need to get rid of that part which just makes a rotation. If that element is moved somewhere, even some parts of the thing may be stretched, but if this element, for some reason, is just moved around here but didn't change the length, then there's also BEU, but there should not be a strain. And that is the reason why we use a combination of the deformation gradient which looks like this. Now I hope I can get the arguments in the right way on the table. There is some mathematical law from geometry. You can split every transformation, whatever you do, in a stretching part, I think it's usually called U, and a rotation part. It's something you always can do. You can say you first make a stretch, then you make a rotation. That can be also always split in this. So if you have this split in mind, what does it mean if we write down F transformed times F? It means nothing more than having the stretching transformed. Technically is a matrix in which the off-diagonal elements are just flipped. We have the rotation transformed, then we have the F, which is just U times R. And now you can rewrite this in a way ut times U transform times U times, just changing order, it's something you can do with matrices. And then we have this times this. And this is interesting, and I'm not sure if one of you is so familiar with this to interpret what is going on here. So rotation is something which we used for the square. You remember we had the rotation matrix. We applied this, and then we made a rotation with the whole thing by theta, by angle theta. So let's say that would be R. That was a rotation matrix. What would happen if you take the same matrix? You could look up at the demo I provided you with the matrix and make the transformed version of it. There were sine and cosine things, and if we flipped that elements and would apply it to the same square. Some of you have an idea what would happen? With R, we make a rotation of phi, and with the transformed version of the rotation matrix, we rotate back. So it's just a reversion, we just do the back rotation. And that means here we get the identity matrix. It cancels out the rotation. And you now maybe understand why it makes sense. That means from the components of the displacement, by using that type of definition here, we cancel out the rotation part, which is not contributing to stretching. We only leaving the parts of the transformation of the movement which really contributes to stretching the material. So that is the main idea. In a way it's a definition, and you may guess why we take minus identity matrix just to get rid of that identity matrix and so on. And this 1/2 is only just a factor. It's also only a matter of definition. So this is what would be the correct way, or that is the way people came up with to defining what is strain. To avoid, I'd like to emphasize and stress again, that you don't calculate strain and accordingly stress by just doing a rotation. There shouldn't be any rotation. And the two squares we were considering in the little chemo, the one used this definition, which cancels out the rotation part, only leaves the stretching part, and the other one is the simplified definition, and simplified that are elements like this, which you conventionally known from your undergraduate studies. That's basically it. Let's work out that a bit more. This is called, I already mentioned before, Green-Lagrange strain. I just noticed last time they took away this name. Maybe they now try to use more simpler name. I forgot. I was surprised when we did this thing last Thursday. Previously it was called Green-Lagrange strain. That is also the name in the literature. Here we have in 3D, no 2D, I only talking 2D, this three strain components, EX, EY, EXY. Why not 4? It is a 2x2 matrix. It's a symmetric matrix. We also may discuss about this, why it's symmetric, we don't do it here. So these elements here off diagonal are the same elements. That is, you act with a force and the material reacts in a different direction. So we need 3 components. 3 are independent in x direction, y direction, and the mixed element, so to speak. And this thing is a vector having, no, it's not a vector, it's a tensor, 2 times 2 matrix, has 3 components, and the components are written here. If you want to understand why it looks like this, we have to work with this. We don't do it in a very intensive way, but just for the one who want to see it once, you don't need to learn this or not remember it, but maybe I give you just the idea how we come up with this. Basically, we just have to make that operation. It means matrix multiplication would be useful to have MATLAB with this or some tool which does it analytically, then you don't miscalculate. Let's just do it. This is the strain matrix, or tensor would be more precise, with the EX, EY, and the mixed elements. They are the same, that's why we just have 3 elements to calculate. And this is just the extensive way of writing what is written here, more confined. Let's maybe start with F. F we have here, and that is that part here. It's not exactly that part. If you compare, there is +1. What happened with the +1 is just because the identity matrix we put in here. You can combine that matrices by addition to 0, 0, +1. So that's obviously F. That one is F. Then minus identity matrix is this thing. Minus identity is this thing, F is this thing. F transformed, if you have F, we come to F transformed by just flipping that off diagonal elements. So U goes here, V goes here. So that's just this thing. And then we have 1/2 in front. So this is just rewriting. And then what we have to do next, if you are interested in EX, what we have to do, we have to do the matrix calculation to get that position. That means that thing, what is this column row? This row combined, the first row combined with the first column. The usual matrix multiplication rule. And that is what results. 1/2 remains. Then this is also simple. I mean, here we have that -1. No, it's not so simple. We have it on here. Maybe just to follow this first row combined with this column means that element is this element times this element, so this times this, plus now this with this element with this element, and then we got a -1 because we're calculating this position and this has -1. And then you can also make further calculations. You can multiply the two brackets, so obviously you get du over dx, du over dx squared. Maybe this is the last thing I try to put an emphasis, the rest I will go through more quickly. But from here you see we get terms which are quadratic in u. U squared, du over dx squared. So remember what we discussed in 1D, which is very similar to what you know about strain, du over dx. Here we have du over dx squared. That is actually the reason why that is called geometric nonlinearity. Nonlinear means we have a higher order term relevant than linear. So you can do the same thing with dy. I think we don't go in much detail in there. It's just the same principle, just some mathematical boring work. You have to be careful not to make a mistake. And then we get these three components. And these three components are exactly what I showed you as a result here. Green-Lagrange strain. This is the correct way to calculate strain. If you use this, the program would never calculate stress if you just rotate a square. So why there's anything else? Because these equations are a bit complicated, aren't they? Not complicated in the sense that the computer cannot solve, but it's just numerical effort. And these things add up. So there are situations when you can make things simpler. When you can make things simpler if the displacement are small, just very small displacements. And for that situations, you can enable in COMSOL to use simplified versions of that exact Green-Lagrange strain formulation. And yeah, what does it mean? If the displacements are small, then it means this du, dv things are small, just small things. And if you have them small and square them, they get even smaller. So that's the usual way you do. You neglect the higher order terms which are quadratic. You can neglect for small displacements. So if you neglect them, then you end up with what is called engineering strain. Maybe they linearize only for small u. Maybe they started skipping because it's a little bit engineering strain. Maybe indicate is simpler, so they don't want to put that label for the engineers in general. But anyway, that's what you do if you neglect the higher order terms. You end up with du over dx. Du over dx, that is what we already found here, and is what people tell you in undergraduate study if they explain the concept of strain. Same thing for the y direction, and the mixed term looks like this. Nonlinear also valid for large. That is always valid, this is exact. If you're sure what you do, you can disable the exact way and just use the simpler version, the engineering strain, and they're very similar for small displacements. To round up, COMSOL uses even a different writing. I don't dive into that again, but this is equivalent to what I wrote here. But at the end, you know, we were talking a lot about the gradient. So you're familiar with this, you are familiar with combining the gradient now even with a vector. Transform is basically the same thing. It's just a different way to write it. And if engineering strain is used, that equations can be for 3D, you know, it was only for 2D. You can imagine it gets even more complicated. You can more lengthy, not more complicated, the equation would look like this. Just to remind you where we started, if we calculate that rotation with this rotation matrix caused by phi, then we would calculate no strain, no stress as expected if we use Green-Lagrange strain. If we use engineering strain, we get a lot of strain, a lot of stress, which shouldn't be there. So you see, you have to think about what is a large, what is a small displacement. That was a displacement, a rotation by 10 degrees, I think so. Is 10 degrees a lot? Obviously, in that sense, more than enough to cause a lot of problems. I thought I have. Maybe it makes sense to appreciate the things we just discussed, to see it in real life, in COMSOL, and then also, I mean, what is the bottom line for all this? I try to explain now, it gives you the background. What you technically have to do is kind of simple. You have to decide whether you put a mark for using geometric nonlinearity, it's just a mark, or if you want to make it numerically more simple, you need to know some things, some adjustments. So that is very simple. You could probably do it without knowing the background, but I think for master level it's nice at least to solve once. You don't need to think about it all the time if you say nonlinearity, but you should have now a background why it can go wrong, and that's an item, and this is something with these details. Of course, I will not ask you in the final examination, but it's just to illustrate things. Maybe some conceptual thing I might ask, but this is something, if I would do, I probably would talk with you again about this. But for the practical part of the thing, maybe it's good to go back to the model. Here we did it. I should have opened before. Sorry for this. Also always takes a lot of time.